Hello, today we finish chapter 10 devoted to apportionment, and we consider paradoxes and other apportionment methods. We start with introducing standard divisor and standard quotient. We have already taught about quarters in Hamilton method. You remember we divided the state's population by the total population to get the percentage of the state's population. Then we multiplied by the number of representatives being allocated. So the state population S divided by the total population and multiplied by the number of representatives. When we multiply a fraction by a number, it means that we multiply the numerator by this number and divide by the total. We can also rewrite it differently, like state's population is multiplied by the number of n and divided by t. If we multiply by a fraction, it is the same that we divide by the reciprocal of this fraction. Reciprocal of this fraction, n over t, is t over n. So this expression, this quota that we calculated by Hamilton method, can be found by dividing the state's population by t over n. State's population divided by total population divided by the number of representatives. When we calculate the standard quota for each state, this expression in denominator will be the same for every state. Only the numerator S will be different. The state's population will be different for every state, but the denominator will be the same, t over n. We call it standard divisor. We divide it, we divide by this number, the state's population. And we actually can use Hamilton method in a smaller number of steps. First, we can calculate the standard divisor and then divide the state's population for every state by standard divisor. So this is another way how to use Hamilton method, and this is how we will introduce another methods. But first, let us work a little bit more with the standard divisor and standard quota. So standard divisor, we repeat, is a total population divided by the number of representatives. We have already used this fraction when we talk about the average constituency. It is actually the average constituency for the whole country, total population of the number of representatives. Standard quota for X is the population of state X divided by the standard divisor. So standard quota is the exact number that the state X deserves. It is a number that has a whole part and fractional part. This is the number that we calculated in Hamilton method, the standard quota of X. Let us calculate the standard quota for this example. Suppose that we want to allocate 8 representatives among several states that have a total population of 4 million. Find the standard divisor, and if state A has a population of 1,400,000, calculate its standard quota. First, the standard divisor. We take the total population, 4 million, divided by the number of representatives, 8, and we get 500,000. This is the standard divisor, and this is the number of people represented by one person, the number of constituents that each representative represents. Now let us find standard quota for state A. We take the population of state A, 1,400,000, divided by the standard divisor from the previous step, 500, and we get 2.8 representatives deserve state A. This is a standard quota and it has its fractional part. Now let us find standard divisor and standard quota for 3 states. Assume that we are apportioning 8 representatives among 3 states, A, B, and C, which have populations 3, 4, and 5 million, respectively. Calculate the standard divisor for the apportionment and calculate each state's standard quota. First, standard divisor. We find the total population and divide it by the number of representatives. So the total is 3 million plus 4 million plus 5 million and divide by 8. 4 plus 3 plus 5 is 12. 12 divided by 8. We can simplify this fraction by dividing by 4 numerator and denominator. It will be 3 over 2 or 1.5. 1.5 million constituents are represented by one representative in each country. Let us now find the standard quota for state A. The population of A, 3 million, divided by the standard divisor. We divide by the divisor by 1.3, and this is 2. This time we got an exact number. So in case that we will use a Hamilton method for this apportionment, we will consider that the fractional part is 0, 0. So the state A deserves 2 representatives. State B, 4 million divided by 1.5 standard divisor is 2.67 approximately representatives. This is the standard quota. It can have fractional parts. State B, state C now 5 million divided by 1.5 is approximately 3.33 representatives. So the standard quotas are 2, 2.67, and 3.33. In using the Hamilton apportionment method, we always gave each state a number of representatives that was immediately below or immediately above the standard quota. So first we assigned the whole part, it was immediately below. And then we possibly assigned an extra representative, then we got the number that is above the standard quota. So we never assigned more than this. So it was either below the standard quota or above, but not more than not more than 1 unit. So this number that is below the standard quota is called lower quota. The numbers immediately above is called the upper quota. So in other words, if we round the standard quota down, we get a lower quota. If we round the standard quota up, we get an upper quota. So, and we can redefine the quota rule if in making an apportionment, each state is allocated a number of representatives that is between the lower quota and the upper quota, then we say the apportionment satisfies the quota rule. So in extremely rare cases that the standard quota is a whole number, is in the last example, use the standard quota for the lower quota and the next high integer for upper quota. In the next example, we assume that we are apportioning 8 representatives to 3 states. States A, B, and C with populations 5.4, 6.7, and 7.3 million. Let us first find the standard divisor for this apportionment. So standard divisor is the total population divided by the number of representatives. First, if we must find the total, adding 5.4, 6.7, and 7.3. 19.4 divided by 8 is 2.425. This is the standard divisor. We do not round it too much. We want to get an answer as exact as possible. So 3 or 2 digits after the point are necessary in such a problem. Then we find the standard quota for state A. Population of A, 5.4 million, divide by the standard quota, 2.425. And this is approximately 2.227. 2.227. If we round it down, we will get 2. It will be the lower quarter. If we round it up, it will be 3. This is the upper quarter for state A. So the apportionment that satisfies quota rule must give either 2 or 3 for state A. Let us find lower upper quarters for B and C. First, the standard divisor, it's the same 2.425. Then the standard quota for B, we divide the population of the state B, 6.7 million, divide by standard quota, and it is approximately 2.76. If we round it down, we get the lower quarter, 2. If we round up, we get the upper quarter, 3. Standard quota for C, we take the population of C, 7.3, divide by standard quota, and we get approximately 3.01. If we round it down, we get 3, the lower quarter. And if we round up, we get 4. Lower quarter, upper quarter. And now let us consider the Hamilton method using the standard divisor and standard quotient. You can use Hamilton method either how we have learned it in chapter 1, section 1, or using standard divisor and standard quotient. So first we find the standard divisor for the apportionment, total population divided by the number of representatives that must be apportioned. Then we multiply, so then we divide the state's population by the standard divisor and get standard quota, the exact number that the state deserves. Then, according to Hamilton method, we apportion the whole part of the standard quota, which is the lower quarter. So in the words that we have just learned, we apportion the lower quarter. And then we apportion the extra representatives depending on the fractional part of state's standard quota. We'll look on the fractional part and decide who deserves an extra. We have already started the Alabama paradox. Now we consider one more paradox, the population paradox. It occurs when the state A's population is growing faster than B's population, and yet A loses a representative to state B. We are assuming the total number of representatives is not changing. We'll consider this paradox on the example of assigning a teaching assistant. So suppose that graduate school at Great Eastern University is using the Hamilton method to apportion 15 graduate assistantships among the colleges of education, liberal arts, and business, based on their undergraduate enrollments. Accordingly, 940, 1,470, and 1,600. So let us use Hamilton method to allocate the assistantships. First, we need to find the total and divide it by the number of assistantships to apportion. So when we add the enrollments, 4,010, and divide it by 15 assistantships, we will get the standard divisor 267.33. Now we find standard quotas for every department. So we divide the enrollment by standard divisor. So for the first, it will be 940 divided by 267.33, 3.52. For liberal arts, we'll get 5.50. For business, 5.99. And according to Hamilton method, we assign a lower quota. So, or the whole part of this number. So 3, 5, and 5. We add them together. And we see that there are 13 seats or assistantships that are assigned from 15. So we have 2 extras, and we decide according to the decimal parts who gets these extras. You see, decimal parts are 52, 50, and 99. 52 and 99 are greater than 50. So education and business should get extra assistantships. So the Hamilton apportionment is 4, 5, and 6, altogether 15. Now the second part, assume that enrollment increase. Education gained 30 students, liberal arts 46, and business enrollment stays the same. Reapportion the graduate assistantships again using Hamilton method. The standard divisor has changed because the total enrollment has changed. Now it is 272.4. With the new enrollment, this was the first part, the previous assignment. Now we have increased enrollment. We find the standard quota for every department. So for education, it will be 970 divided by 272.4. It is approximately 3.56. For liberal arts, 5.57, and for business, 5.87. Then we assign the whole part, which is the same as lower quota. And then we look on the decimal parts. So, and first we must decide how many extras do we have. 3 plus 5 plus 5 is 13, so we have 2 extras. And now the two greatest decimal parts are 57 and 87. Liberal arts and business get extra assistantships. Now, education lost the assistantship, even though the growth was relatively bigger by education than by liberal arts. Another paradox that can occur by Hamilton method is new state paradox. New state paradox occurs when a new state is added to and its share of seats is added to legislature, causing a change in the allocation of seats previously given to the states. It happened, for example, in 1907. Before Oklahoma joined to the country, House of Representatives consists of 386 seats. New York had 38 and Maine had 3 seats. Then Oklahoma joined. We used the standard divisor from the previous apportionment when it was 386 to determine the standard the quota for Oklahoma. It was 5, so 5 seats were added to the legislature, and 391 seats were apportioned, and then New York lost 1 representative and Maine gained 1 representative. So it represents a new state paradox. So the apportionment changed, but their population of New York and Maine before adding this 5 representative was the same. We will show how this new state paradox can occur on another example. A small country N consists of 3 states A, B, and C with populations given in the table, and the legislature has 37 representatives. Apportion the representative using the Hamilton method. So we find a standard divisor, total population divided by the number of representatives, total population given here on the table, and then we divide this population of each state by the standard divisor, find the exact quotas deserved by each state, apportion first the whole numbers or the lower quota, and then the sum is 36, so we have 1 extra to apportion, and it goes to the state B, since B has the greatest fractional part. Now suppose that N annexes the country D with 3,000 population, and give D the current share of representative using the standard divisor of the current apportionment, and add this number to the total number of representatives of N. So the standard quota of D will be 9.14. So we add 9 representatives to the legislature. So now we have 37 plus 9, 46 seats to apportion, and the population also increased by 3,000. The new total is 15,140. So the new standard divisor is 329.13. We reapportion using this standard divisor and using 4 states. So that standard quotas are 8.36, 18.35, 10.18, and 9.11. We first assign the whole part or the lower quota. We count them together, get 45 seats. The total, the number of seats that we want to assign is 46, so we have 1 extra. And then we consider the fractional parts. They're also given in this column. 36, 35, 18, and 11. 36 is the largest fractional part. So the state A gets an extra. So 9 representatives. And if you compare with the previous slide, then you will see that B loses 1 representative when another country is added to the country. So by adding D and increasing the size of legislature according to the number of representatives that it deserves, B had to give 1 of its representatives to A. This illustrates the new states paradox. There are also other apportionment methods, and they use trial and error and to find the modified divisor d sub n. We will consider three methods: Jefferson, Adams, and Webster's. And the difference between them is how they round the standard quota. So Jefferson method rounded down, Adams method rounds up, and in Webster method we use the usual way to round numbers. And so we round the quotas down, and if you round the quotas down, of course we will get the number, the total number less than we want to assign. It means that we must modify the quota. And so we change the quota by hand, so we don't have any formula for this, and we change until we get the number to assign that we need. So let us consider this Jefferson's method on the example from the first section with the consortium board. We have three companies, A, B, and C, with a total of 10,000 stockholders, and we want to assign 9-member board. So the standard divisor is 10,000 divided by 9 is 1,111. If we use the Jefferson method, we assign the lower quota 4, 3, and 1. The total is 8. So how should we change the standard divisor to get 9? So if we use the standard divisor, then we get the quota less than needed. If we decrease the standard divisor, then the quotas divide by this number. The quotas will increase. So we will decrease the standard divisor a little, step by step, to get what we need. So we start with the standard quota, and so if we take the lower quarters, then we get 8. Let us modify the quota. We want to make it a little bit smaller, so that standard the divisor a little smaller, so that the quotas will be greater. Instead of 1,111, let us take 1,050. We divide each state population by 1,050. We get new quotas, and again we assign the lower quota the whole part, and we still get 8. It means that we must make this number a little bit smaller, smaller. Let us take 1,000. We divide each population by 1,000. So here 4,700 we divide by 1,000, get 4.7, 3.7, 1.6. Adding them together, we still get 8. So we must make it even smaller. Let us take 950. This time we get 4, 3, and 1, still 8. And we need it even smaller. Let us take 935 for standard quota. And now we get 5, 3, and 1 added together. They give 9, the total of 9. So this is the apportionment according to Jefferson method. 5 representative go to A, 3 to B, and 1 to C. On the last column, we have also the Hamilton's method to compare. You see it a little bit different. So, and modified divisor for this apportionment is 935. This is the divisor that we use to apportion the representatives. Adams method, all the same, but we round up. So if we start with the standard quarter, if we round the sum up, it will be 5 plus 4 plus 2 will be 11. We need 9. So to reduce these numbers, we must increase the divisor. So let us take 1200. Now, if we round it up, we will get 4, 4, and 2. The total is 10. It is still more than 9. So we will increase it a little bit more. Take 1300. Now the quarters, the modified quarters are 3.61, 2.84, and 1.23. We round them up, 4, 3, and 2. The sum is 9. So we can take this modified quarter for Adams' method. We can compare it with Jefferson's method and Hamilton's method. You see, it's the same as in Hamilton. It differs from the Jefferson's method. And the modified divisor for the Adams' method is 1300. And the third method, Webster method, we use usual rounding. So first we start with standard quarter. Standard quarter for A is 4.3. We round it to 4. 3.3 rounded to 3, and 1.44 rounded to 1. So the total is 8. So we must modify the quarter, and we want to get a greater number. So the divisor must be a little bit smaller, and we take, instead of 1111, we take 1000. Then the quarters will be 4.7, 3.7, 1.6. 7 is rounded up, so it's approximately 5. 3.7 is approximately 4, and 1.6 is approximately 2. 5 plus 4 plus 2 is 11. This is great and needed. So we will increase the standard divisor. Let us take 1050. Now 4.48 is rounded to 4. 3.52 is approximately 4, and 1.52 is approximately 2. Adding them together, we get 10. Still a little bit bigger than needed, so we will increase it a little bit more, make it bigger. Let us take 1060. And now when we round the standard, the modified quarters, 4.43 will be rounded to 4, 3.49 so 3, and 1.51 rounds to 2. The total is 9. That is what we needed. So we can stop here. Webster method gives the same apportionment as Hamilton method and Adams method, 4, 3, and 2. And it differs from the Jefferson method apportionment. For Webster method, we got the modified divisor 1060. So the number of voting seats in House of Representatives is currently set at 435. It has been this since 1913, except for temporary change in 1959 after Alaska and Hawaii were admitted into the Union. You see on this picture how the allocation of congressional districts changed after 2000. census, and after 2010 census, you see that Texas is growing very fast. It gained more than 2 seats. After 2000 census, it was 32 seats, and it gained again 4 seats after 2010 census, and you know that now the population is grown again, and will possibly change after 2020 census, and the congressional districts will be redistrict for Texas again. Okay, thank you. We finished the chapter 10. Thank you and bye.